to speak at the conference, and of course I want to say happy birthday to Lou. So it is a great honor that I can personally greet him at this occasion. So, and there are two pictures here in front. One is probably not very original, so I have seen some other people using that picture, but it is kind of Lou in his most natural way. The other picture that is on the right, so maybe I say a few words about this at the end, but I emphasize that this picture is not web downloaded and is not AI generated or anything. So it is a real picture which I took with my cell phone some years ago. Okay. But let me first move to just a moment. To the title page. So this is mostly work joined with Hua Zhongli and Gyotek Jin from Dongguk University and from KAIST respectively. And I will start with some, so here is a table of contents. So I will say some basic definition, and then I will make a small remark about upper bound of crossing number for not in terms of arc index. Then I will talk about NUTS construction, which gives an equivalence between grid diagrams and band presentations, and then say something about quasi-positivity and strong quasi-positivity of Whitehead doubles. Then I will introduce the main tool that is behind some of these proofs, which is the Hornfly polynomial, which gives a number which I call L, which is the lower bound for the arc index. And then at the end, I will discuss some special case, the special case of torus knot, which is kind of joint work with Vivek Singh in Abu Dhabi, and maybe then mention some open projects. So here are some basic definitions. I don't want to spend too much time on this. So the crossing number of a diagram, the number of positive and negative crossings, and when you smooth the crossings out, then you get Seifert circles. So W is the right, S is the number of Seifert circles, and C of K, I denote the crossing number of cages for reference later. So this should be fairly standard definitions. Then there is this arc presentation, which I have been considering for some time, where you embed a knot into an open book such that on every page there is an arc which connects with the axis. And then the smallest number of pages that you need to represent a knot in this way is called the arc index. And I already make this remark here that the arc index is known, at least for knots. I don't know exactly about the case of links. If somebody knows, then maybe you can tell me. But at least for knots, it is known that it is 2 subadditive on the connected sum. So the sharp means, of course, connected sum. And this follows from some results of Toris, Wetnar, Honda, and Dinikov and Prazov some years ago. So, a way to formalize grid diagrams is also, you can say a grid diagram is something that you can build up in the plane in a style of like Kaufman or Monaco using this style. So you have these rectangular angles, you have the strands up and down, and the important restriction is that at crossings, always the upper strand is the one which is the vertical one. Okay, so and then you can formalize the definition of a grid diagram in terms of this mosaic, and it is not very difficult to see that every knot has a grid diagram and that arc presentations correspond one-to-one to grid diagrams. So whether I will mostly talk about grid diagrams, not about arc presentations, but they are kind of equivalent. So then I fix some notation regarding braids. So I consider the braid group Bn with Artin generators sigma 1 to sigma n minus 1. And convention will be now that braids are oriented from left to right and the strands are numbered from top to bottom. Okay, so sigma 2 is the Artin generator which crosses strands 2 and 3 positively. Sigma 1 inverse is the generator which crosses strand 1 and 2 negatively. Okay, and then there are the obvious relations. So sigma I plus 1, sigma I plus 1, sigma I plus 1. and sigma j commute if the indices are at least 2 apart. Okay, and you can regard, so when you write a braid with Yartin generators, then you can regard the closure, which is a link, as a diagram of the link, and the rise of the closure diagram is the exponent sum of the braid, and the number of Seifert circles of the closure diagram is the number of strings of the braid. So this is a well-known relationship. This is sometimes useful to keep in mind. Then I'm going to speak about quasi-positive and strongly quasi-positive. So quasi-positive braid is a braid which is a product of conjugates of the Yartin generators. And so this was studied in terms of, because of algebraic curves by Rudolf, Boileau, Revkov, and some other people. And the closure of a quasi-positive braid is a quasi-positive link. And if we restrict these conjugates to be what is called embedded bands, like in the below picture, then so you get, and this is then called a strongly quasi-positive braid, and the closure of a strongly quasi-positive braid is called a strongly quasi-positive link. Okay, and so these band generators that you obtain, they are kind of generalization of the Yartin generator, except that you connect strands which are not neighbored. Okay, so the band generator sigma ij is the generator which connects strands I with j as a positive band. And when j is I+1, then you get simply the ordinary Yartin generator. And so in this example, this is the band which connects strands 2 and 7, where I remind that I count the strands from top to bottom. Okay, so this is the band generator sigma 27 in B9. Okay. And now these band generators, they give a presentation, and then you can study them in a group theoretic way. So this was done by Berman, Cole, Lee, and then but I do not get into this too much. Rather, I'm interested here that whenever you have a band presentation, so when you write a braid in terms of the product of generator, you get a Seifert surface of the link, which is obtained by you make a disk for every braid strand, and then you put a half-twisted band for every band generator. Okay, so in this example, you have a 6 braid with 6 bands, 1, 4, 3, 5, 2, 4, 3, 6, 1, 5, 2, 6, where you read the band generators from left to right, and the strands are numbered from top to bottom. Okay, so so for example, this here, okay, this will be sigma 1, 4, okay, and this here sigma 2, 6 will be this one. Okay, so let's see where can I still, okay. So, and once you have this, then so you can say you have a braided surface, and if you have a braided surface which is minimal-genus, then the Bierman and Menasco coined this terminology, is called a Bennequin surface. So and if the braid word is positive, then you call this a strongly quasi-positive surface. So and now there is this Bennequin's inequality, which relates the Euler characteristic of the closure in terms of the right hand of number of Seifert circles. So minus the Euler characteristic is big equal to right minus number of Seifert circles. And it is very easy to see from that when you have a strongly quasi-positive surface, then it is minimal genus, so it is a Bennequin surface. So you say that the link is Bennequin sharp if this Bennequin inequality can be made into an equality for some proper braid representative of the link. So so obvious consequence of this is if L is strongly quasi-positive, then L is Bennequin sharp. And now there is this problem about the equivalence of the two. So this is not known. There is this problem that L Bennequin sharp is equivalent to strongly quasi-positive. So I will talk about some applications to this problem later. So the other thing that I consider is braid index. So this is the minimal strand of a braid representative, and I define the Bennequin braid index to be the minimal number of strands on which you can span a Bennequin surface. So a minimal genus surface in a band form. And similarly, if the link is strongly quasi-positive, then you can consider the what I call the strongly quasi-positive index, which is the minimum number of strengths to span a quasi-positive surface. And since every quasi-positive surface is a Bennequin surface, and every Bennequin surface gives a bright representation, obviously you have these inequalities. And with Hirasawa some time ago, we gave some examples that the Bennequin breakings can actually be higher than the breaking. So this means you cannot span a Bennequin surface on a minimal string breaks. But there is this question of Rudolph whether the strongly quasi-positive breaking is actually equal to the breaking. So this means if you have the link is strongly quasi-positive, can you always span a strongly quasi-positive surface on a minimal string braid? Yeah, and that question is open, and I will again talk about some applications to the question. So for example, we know that it is true for all the strongly quasi-positive nodes up to 16 crossings. This now is kind of just a remark that once you have a grid diagram, you can get some bound on the crossing number. The interesting thing is that I never found anywhere in the literature any upper bound of the crossing number in terms of the arc index. The other way around it exists, and I will talk about it later. But so if you bound the arc index then to give an estimate of the crossing number, this was apparently never written down. So there is a remark. You get this kind of a quadratic bound, and we know by looking at torus links that this bound is sharp up to a factor of 2. But what happens with this factor of 2, we don't know exactly. So this bound is just by counting the number of intersections of a planar rectangular polygon. But we don't know how much we can improve it if we allow to. So I mean, these grid diagrams then can be manipulated by Cromwell moves, and how much you can use Cromwell moves to reduce this crossing number, we don't know exactly. So this is kind of a little bit of an old problem, but I'm not going to talk too much about it. So rather more important is what I call here nuts construction. Okay, so let me write for AKT for the T twisted annulus around the node K. And so the convention here is that T is the linking number of the two components. Okay, so there are two conventions for this for this framing. The one is our convention, and the other one is the convention you take the right of a diagram from which you build a blackboard flame parallel. But if you do that, then you get the opposite sign, because if you have a positive crossing, then you build the blackboard frame reverse parallel, then it gives you a linking number -1. So keep in mind that our convention here is that T is the linking number. Okay, and now there is this construction which was observed by Nutt. Whenever you get a grid diagram, you can always make a band presentation out of it, where you simply treat the extension of the horizontal segments as braid strands, and every vertical segment gives you a band. Okay, so whenever I have a grid diagram D, I can make a braid beta D out of that grid diagram, and that gives me a band presentation of what? So now it's very easy to see that this is an annulus around the node. So it is a band presentation of AKTD for some number TD, which is associated with the diagram D. And now the question is, what is TD? And what it turns out to be basically the Thurston Bennequin number. So you can define the Thurston Bennequin number for our purposes as the right minus the number of northwest corners of the grid diagram, or southeast corners. Okay. So, and then it is not too difficult to observe that this framing is minus the Thurston Bennequin invariance. Okay. So, and so in contact topology, sometimes they study this maximal Thurston Bennequin invariant of knot, which is the maximal Thurston Bennequin of all Legendre embeddings. Yeah, now what we get out of this here is, so let us define lambda T to be the minimal T so that AKT is strongly quasi-positive. Then this minimal framing of a strong quasi-positive annulus is minus the Thurston Bennequin invariant. And the annulus strongly quasi-positive if and only if T is bigger or equal to minus Thurston Bennequin. So there is this identification of the lambda number with Thurston Bennequin invariant up to sign, but since I used lambda number a lot in the following. So I will not write minus TB. I will keep the sign my way around and continuously write lambda. Okay, you must be careful. For the unknown, there is a little bit of difference, but this is basically because whenever I have a quasi-positive brane representation, I can go back in Nuts construction to a grid diagram, but this doesn't work for the empty band representation of the two-component unlink. This is why for the unknown, there is a little bit of difference. But otherwise, simply think of lambda of K as the negated maximal Thurston Bennequin invariant. So now there are some results. I need to remark the following. There is a result by Dinnikov-Prasolov that the maximal Thurston Bennequin invariant is realized in a minimal grid diagram. And what you get from this, for example, is the following: lambda K plus lambda of the mirror image of K is equal to A of K. So they have this kind of mirroring property. And another thing that you get from this is that since the lambda of K is realized in a minimal grid, by Nuts construction, you get a braid with A of K strands. So the braid index of this particular framed annulus is at most A of K, of course, which is less than equal to if you minimize this further. And the conjecture is that they are actually equal. So the conjecture is that the minimal braid index of every reverse annulus is equal to the arc index. Okay, now we'll talk about this conjecture sometime later. So here is a useful remark on this from this situation, that obviously when you have a braid representation of the reverse annulus, it is bigger equal. It has at least as many strands as the sum of the braid the strands of the braid representations of the two components, which are both K. And then from here you get very easily that 2B of K, so twice the braid index, is less than equal to the arc index. This was also observed by Cromwell. The interesting thing about this is that if you combine this with the upper bound of the arc index that was obtained by Bay and Park, you get then Okuyama's braid index inequality. So this is another completely different way of proving Okuyama's braid index inequality. The braid index is less than equal to the crossing number of K over 2 plus 1. But since for non-alternating, Jin and Park improved this bound, so Bay and Park, and so C Park is Chan-Yong Park. I know him. Who is W Park? I do not know. So keep in mind that 9% of Korean population are called Park. So there are more Parks in Korea than there are mathematicians. So if you like to know who is W Park, please ask Professor Jin. Okay. So anyway, Jin and W Park, they improved this result for non-alternating. Again, a consequence of this is that you get actually an improvement of Okuyama's braid index inequality when you have a non-alternating node. So in that case, this plus 1 can be omitted. So the braid index is actually less than equal to crossing number over 2. This is something that you cannot get from Okuyama. But this is just a useful remark. In general, it is not the best idea to simply look at the components individually, but rather you better look at the whole link. Okay, and next thing that I'm going to discuss, I introduce some results about strongly quasi-positive Whitehead double. So now strongly quasi-positivity and quasi-positive, they depend on mirroring. So you have to be careful. You have to be careful with both the framing and with the sign of the clasp. So there is positive clasp Whitehead doubles, which are at W plus, and there is negative clasp Whitehead doubles, which are at W minus. Okay? And they both have a frame. So, a way of constructing a bent presentation of the Whitehead double is simply you take a bent presentation that you get from Nuts construction, and then you double a bent. You just must be careful that you double a bent of the right sign. So if you want a positive clasp Whitehead doubles, you have to double a positive bent. If you want a negative clasp Whitehead doubles, you have to double a negative bent. Okay, so now first question is, when is this strongly quasi-positive? And now the answer is relatively straightforward if you use Rudolph's result about Murasugi sum. So the answer is W minus is never strongly quasi-positive, and W plus is strongly quasi-positive if and only if T is bigger or equal to the lambda number, so minus Thurston Bennequin. So this is relatively easy, but this is a nice consequence of Rudolph's result on Murasugi sum. The question about quasi-positivity is far more interesting, okay, and much more complicated. So we cannot decide this in full, and it doesn't seem to be very easy. So what we know, for example, is the following: that equivalence of quasi-positivity and strong quasi-positive holds for W plus when K is alternating. Okay, when K is alternating, HW plus is quasi-positive if and only it is strong quasi-positive. And this uses a lot of stuff. So it starts with L sharpness that I'm going to talk about below. And then I use Hedden's evaluation of the jump number for the tau invariant and some version of Kesson-Gordon invariance, which was due to Gilmer and was explained to me recently by Chuck Livingston. So all of this kind of plays a role, and the Kaufman polynomial also plays a role. Okay, so there is this jumble of tools that enter into this. And I immediately warn, okay, so we found some examples with Stepanov Revkov that in general, the positive class Whitehead doubles can be quasi-positive, but not strongly so. So when K not K is non-alternating, then it is not necessarily the equivalent. Okay, so this is non-trivial problem. What happens with W minus, we mostly suspect that none of this is quasi-positive. We do not know this completely, but we know most of it. So we know for every node there is at most one framing where this can be quasi-positive. So for example, for the unknot, it can be 0. Okay, but in general, we cannot. We know there is at most one T, and we can rule this single value T out in some cases. For example, when K is alternating or quasi-positive and not slice, then we know that all the W minus are not quasi-positive. And there is also a result for amphichiral case. So when you have an amphichiral knot and W minus is quasi-positive, then we know that T is equal to 0, so which is not very surprising. So it can only be the untwisted Whitehead double. And what the other thing that we were able to get is that the Honfly polynomial of the negatively twisted Whitehead double is trivial. Of course, this is not a way to construct a knot with trivial Honfly polynomial. I mean, you take an amphichiral knot and then you assume that somehow prove that W minus is quasi-positive, and then you know that the Honfly polynomial is trivial. Of course, this is you can use it as an abstraction. This practically says that for amphichiral knots, this is also excluded. Okay. And now we can also reproduce the Livingston-Naik result about the jump numbers of Staios-Torus invariants. I have no time to discuss now. But for example, we have then an application which is that for if you have a positive knot, then the Bennequin sharpness problem for the Whitehead doubles is resolved. Okay. This is also true for alternating K, but for some other reasons, maybe depending on how much time I have, I will say. So now here is the main tool that I'm using, and so I'm using the Honfly polynomial in these variables v and z, and so which are mostly used by Morton. And I define a quantity which I call L, and L is kind of like the bound in Morton-Franks-Williams for the untwisted annulus, for the twisted annulus, but I have to choose the framing properly so that the degree, minimal degree in V is negative and the maximal degree is positive. So I didn't say this, but it is well known that when you have an even component link, then the powers on V and Z are odd, so they cannot be 0. And when you have an odd component link, like for a knot, then they are all even. Okay, so. And it is very easy to see that T can be chosen this way. And now you have to prove that it doesn't depend on the choice. And there is also a way to compute it when T is not chosen this way. So so this is kind of, you get a pen and then you have to trim the pen handle from the pen. Okay, so Anyway, you can define this number. And this number gives a lower bound for the arc index. And we do not know whether it behaves well with respect to connected sum like the arc index. Thus, we expect this to be the case, but we cannot prove it. But we can compare this bound to the Morton-Beltrami bound, which is the span of the Kaufman polynomial plus 2. Okay, and there is evidence that our bound is generally better. So we know this for torus knots, alternating knots, and we can also check it up to 16 crossings. So this, so in many cases, L gives the exact arc index, and let us call the knot L sharp in that case. So we know that up to 10 crossings, the only prime knot which is not L sharp is 1032, and then there are 4 examples with 11 and 21 examples with 12 crossings, but for many knots it is L sharp. And in particular, since we conjecture that L is bigger, is at least as good as the Morton-Beltrami bound, for an alternating knot, it is known that Morton-Beltrami bound is sharp. So our conjecture would have to imply that for alternating knots, our bound is also sharp. And now this was proved. So it is kind of proved by Diao-Morton, although actually they proved something else, but their paper contains the main ingredients to prove it. So and here is our generalized version of Diao-Morton. So this is an explicit formula for the Breit index of the reverse parallel, depending on the framing for an L-sharp knot. So you can express this Breit index in terms of the arc index and the maximal Thurston-Bennequin invariant. So what this formula basically says is if T is very small, then the Breit index is very large, and when T increases, then with every T increasing, this goes down by 1 until it reaches lambda k minus A of k, then it stays equal to A of k until T is lambda of k, and then it starts going up again when you increase the frame. So it is kind of a trapezoidal picture. So, okay. And from this, you can, of course, prove, so this implies that the minimal Breit index is big equal to the arc, so it's equal to the arc index, so this is conjecture 20. And you can also resolve the question about minimal string, strongly quasi-positive surface and the Bennequin sharpness problem for the reverse annual for the untwisted Whitehead doubles. But if for the minimal string Bennequin surface, there can be a problematic value. So maybe I should emphasize anyway that, I mean, it's not like everything is falling from the sky, so everything is immediate. So there are some nasty examples for Whitehead doubles where you cannot determine the Breit index properly, and this family contains the pretzel knots K3 minus 3. So they of course always slice, and then if you take the untwisted Whitehead double is also slice. So they are difficult examples to resolve this issue. But for example, in case alternating, then this problematic value T can also be avoided. So for alternating, also the negative twisted Whitehead doubles have a minimal string Bennequin surface. And here is some. So what can you say about the Thurston-Bennequin invariant? Now there is this bound of the Thurston-Bennequin invariant, which comes from the Kaufman polynomial, which is kind of, I don't know exactly the history, but so it was popularized by Fuchs and Tabachnikov, and then also appears in work of Emmanuel Ferrand, Toshifumi Tanaka, and some others. I don't know how to call it, but luckily Ferrand and Tanaka kind of seem to have the same first letters of the family names as Fuchs and Tabachnikov. So kind of with F and T, we can more or less specify properly who is involved in this bound. So this is the bound 1 minus minimal degree of the Kaufman polynomial. So keep in mind that lambda is the negated Thurston-Bennequin invariant, and our convention for Kaufman is that the right-hand trefoil has positive degrees in A, okay? And now it's very easy to see because of the mirroring property of the Kaufman that Ft of k plus Ft of mirror image of k gives the Morton-Beltrami bound. So this is something similar to, you think here. if you go back to this property, okay, and to this property, which so this mirroring property is true also for the bounds, for the FT bound. Okay. So when you sum it with its mirror image, you get the bound for the arc index. And we can now define a number theta, which kind of refines our lower bound for the index in a similar way. So it is a lower bound for the Thurston Bennequin invariant, and when you sum it with its mirror image, you get the lower bound for the arc index. Okay. So in particular, you can very easily see that when the knot is L sharp, then theta gives exactly the Thurston Bennequin invariant. So and now the conjecture is again that theta improves the FT bounds in the same ways which L improves the Morton-Beltrami bound. So you have a picture like this. Okay, so this means we have our own copy of this FT Morton-Beltrami business. Okay, and we conjecture that ours is at least as good or something like that. And we have again verified this for some number of knots. So and now there is some further methods, because the L invariant is not, I mean, it's not almighty. Okay, so but we have further tools. We can use cabled polynomials, but then we have to truncate in order not to make this too slow. Okay, and we can determine the maximal Thurston Bennequin invariance and arc indexes up to 14 crossings. For 13 crossings, it is submitted to Chuck Livingston on Notinfo. 14 crossings you can find on my page. Okay. So now in the last minutes, I say something about torus knots. So it's an interesting special case of our situation. So when you define TPN to be a torus knot as a closure of sigma 1 to sigma p minus 1 to the power n, so it is positive, and I assume that n is bigger than p, and mostly assume that p and n are relatively prime. So then there is this result of Etnayer Honda that arc index is TPN is p plus n, which is very nice result. And they have they have a geometric proof. The less than or equal is easy, so you can easily find an arc presentation. The problem is to prove this is that there's nothing less. Okay, and because this problem is kind of equivalent to proving the maximal Thurston Bennequin invariant of the negated torus knot, which is equal to Pn. Okay, so. And our question is, can we use our approach to do this? So what happens with use Kaufman polynomial? Then there is this formula by Yokuta and Labastida Perez for explicit formula for the Kaufman polynomial torus knot. And you can see from that for P even, the Morton-Beltrami bound gives the arc index, but it fails very badly when P is odd. So this then gives not P plus n, but 2P. This means when P is odd and I make n very large, this remains constant, while of course the arc index grows. Okay. So let me skip this here. So, so anyway, the Yokuta-Labastida Perez formula shows that Morton-Beltrami works when P is even. When P is odd, it doesn't work very well. So what happens when we use our invariant L? And now, so it is important here to fix this framing. So when I take TPN, I take the framing minus P minus 1n. So this means it's like I take the ordinary bright presentation of the TPN torus knot, and then I take the Blackford frame reverse parallel. Okay, so what happens like for P3 and N4, it looks like this. And then it appears that the Hornfly polynomial has the following form. It has a part which is in degrees between 1 minus 2p and 2p minus 1. So this is what I write with this. Oops, sorry. So this is what I write with this part here. So this is something in degrees 1 minus 2p 2p minus 1. And then there is this term which contributes higher powers of v until 2n minus 1, always in degree z, so no higher power of z appears, and the coefficient is always 1 minus p. So now it looks like a panhandle. So if you look at why doesn't this work? Ah, okay. So if you see this example, you see that there is this minus 1, minus 1, minus 1 that occurs on the right, and this is what this purple term contributes. Okay, so this is kind of a panhandle, and the conjecture is that this always occurs. So this in particular would imply that the TPN is L sharp. So this means you could reprove the Edna Honda result with our methods. Of course, they prove other things. So they prove, for instance, that the Legendrian bending is determined by the Thurston Bennequin number, etc. But anyway, the goal was not to reprove everything, but just to create something which fits well into known theory. So, and if we prove this conjecture, then we will have that. So what we know, we certainly know that L is bigger or equal to the Martin-Beltrami bound. So that piece is certainly there. And we know the cases 2 and 3. Okay. So where for 2, I use some skin algebra programming, and Vivek, so who I'm working with in Abu Dhabi, he proved the case P is equal to 3, and more or less he knows what happens for the IRP, but we are going to work it out. So this is kind of work in progress. And I emphasize that for Pn not relatively prime. So this means when you have torus links, then the situation is more complicated. Then the panhandle is not that nice, and we maybe consider this later after we finish the knot case, but this kind of next plans. Okay, and here are some simple directions of further research. I should emphasize that L invariant so far really works only for knots. So you have to modify this somehow for links, but so this remains work to be done. Then, as I mentioned, this problem to improve the upper bound of the crossing number in terms of the arciness, if we can get, and then maybe the question, what do you do for braided surfaces of higher Euler characteristics? So this whole story started with my desire to understand how does a braided surface look like, and I started with the simplest non-trivial case. Okay, and this turned out to be already very complicated, but this gives many applications to grid diagrams. Now you can generalize it to, so how can you formalize this further is grid diagram. You generalize this by saying you allow these triangular crossings. But of this form. So of this form, but not of this form. Okay. So when you want strands go from left to right and bends go to up and down, then you can allow the first type of the crossings and the other one not. Okay, so now thank you very much, and I just say, as I promised, just a couple of words about this picture. So as I said, these pictures were not AI generated, and I have not downloaded them. So these were physical things that I have. So I have held this in my hand, and I have hanged this myself on the tree. So I was walking in the park some years ago, and then I found this hanging on the tree. So you can see this on the left. This is how it was original, and then I hang this so this looks a little bit nice, and I made some photos and put it in my archive to be used. And okay, now since Lou Kaufman has 80th birthday, I thought I can illustrate it in this day. So thank you for listening, and let me say one more time, happy birthday to Lou. Thank you.
Yes, thank you very much. Very interesting talk. So are some questions, remarks, or comments?
So can you hear me?
Yes.
Okay. You made a comment about wanting to know the behavior of the arc index under connect sums for links.
Yes.
That was proven by Cromwell in his 1995 paper. It's the same formula as what you presented for knots.
Okay. Thank you. Okay, I didn't know that. Okay.
Mm-hmm.
Okay, thank you. Please, more questions? I would like to ask a simple question about your discussion about torus knots. So you told that it's difficult to generalize for links. So what is the problem?
Well, the formulas do not look that nice. I mean, so first of all, I think that Labastida-Perez Yokuta formula works only for knots. Okay, so that restriction is pretty essential. And then a similar situation is if you want to do this for the reverse home fly, then this Rousseau-Jones formula that my collaborator is using, it also restricted to knots. So there are ways to make this work for links, but it's more complicated. And so you by any means